Hi, I'm Dr. Papia Bhattacharjee. In this problem, we are given this particular series, this infinite series. We have to determine if it converges or diverges. Okay, so recall what have we learned so far? What type of series did we see so far? Well, we have seen geometric series, and we know that there's a test of convergence and divergence for geometric series. And we have seen the nth term test. Those are the two tests so far. Now, to test a series, if it converges or not, is kind of beneficial to first notice if this particular series is known to you, if it looks like one of the known series, like a geometric series or not. So the first thing you should think about, is this series geometric? Well, remember, geometric series has the form a times r to the n. Does it look anything like a times r to the n? Of course not, because for a geometric series, the n, the variable, is in the exponent. And here, all the n's, they're not in the exponent. So this is not a geometric series. So that's the first thing you should notice. Why? Because you cannot apply the geometric series test to this series because it is not geometric, right? So what do we have left? The nth term test. So why don't we apply nth term test to this series and see if we get any result, right? Okay, so remember nth term test. If you have a series an, okay, say n equals 1 to infinity, you take the limit of an and see what happens to the limit. If the limit is not 0, only then you know that the series diverges. So this is a test for divergence only. Okay, so let's apply that test to this particular series. So we have series n plus 1 over 2n minus 1, which means this entire expression is an. Okay, so it's looking like series an. Now let's compute the limit of an as n approaches to infinity. So we are computing limit of n plus 1 over 2n minus 1 as n approaches to infinity. So how do we evaluate this limit? Look, there's n both in the numerator and denominator. This is actually a rational function. And recall, when you have rational functions, there's one way we can evaluate this limit. So look at the highest power of n, both in the numerator and denominator, and it's 1, right? N has the power 1, that's the highest. Now divide both numerator and denominator by n to the power, the highest power, which is 1. So let's do that. We're dividing both numerator and denominator by n. Okay, so what do we have? Let's simplify the expressions. In the numerator, divide each of these terms by n. So we get n over n plus 1 over n. Let's do the same for the denominator. So 2n over n minus 1 over n. And see, we can simplify it further. So we will have n over n is 1, and 1 over n, keep it as it is. In the denominator, we have 2n over n, so the n cancels and you get 2, and then we have negative 1 over n. Why did I do this? Because I know this n is approaching to infinity, so 1 over n will always approach to 0. Because the denominator is getting big, entire thing will get small. So we know this term will approach to 0, and this term will also approach to 0. So finally, we will then have limit of 1/2 as n approaches to infinity, and that is 1/2. Okay, don't forget what we are doing, right? We are applying nth term test. And what do we want to see? we want to see if the limit is not 0. And that's exactly what's happening. The limit is 1/2, therefore it's not 0. So nth term test will tell us, so this means by the nth term test, series diverges since the limit is not 0. Okay. Now, this concludes the first part of the problem, that we have concluded that this series will diverge using nth term test. So, to finish the problem, we have to verify this result using a symbolic algebra utility. Now, note that if you plug this entire series in an algebra utility, it will tell you that the series will diverge. But to prove it, there is one way of looking at it is, remember what the basic idea of sum of a series is? It is the limit of all those little partial sums. Remember that? So what you can do is, you can see the graph of the partial sums to this series. And you will see that that graph will actually keep on increasing. And it will not approach any particular value. It will not tend to go to any value. So it will keep on increasing. And you will see that when you plug in this function. And therefore, the partial sum increases and keep on increasing. That means the entire sum will actually be infinity. So that is a way of verifying this result using the algebra utility. So that concludes this problem. Thank you.